All right, welcome. Today, we're going to dive into the world of some seriously versatile and, yeah, sometimes controversial molecules in organic chemistry. Haloalkanes and haloarenes. You could call them the quiet workhorses of the chemical world. They play these hidden but absolutely critical roles all around us. So let's find out what they are and, more importantly, why they matter so much. So to kick things off, let's start with a little puzzle. What could possibly connect a powerful antibiotic, one that fights life-threatening infections, with a vital hormone that your own body produces to keep your metabolism in check? I mean, the link seems kind of impossible, right? But the answer is hiding in plain sight, right in their chemical structure. And that's exactly what we're here to uncover. And that right there, that's where our unseen overachievers come into the picture. The answer to our puzzle? It lies with a special family of organic compounds that all have halogen atoms. And trust me, they are absolutely everywhere, doing critical jobs that we pretty much take for granted every single day. And here it is, the big reveal. The connection is a halogen atom. You know, fluorine, chlorine, bromine, or iodine. That antibiotic, chloramphenicol, it's got chlorine. The hormone thyroxine, it has iodine. And as you can see, the list just keeps going. From chloroquine fighting malaria to halosane used as an anesthetic in surgery, these compounds are, quite literally, lifesavers.
But beyond medicine, their usefulness is just staggering. Seriously, in chemistry labs and in huge industrial plants, they are completely indispensable. They're great as solvents, and maybe most importantly, they're the foundational building blocks, the starting point, for creating a massive variety of other organic compounds.
So, to really get a handle on these molecules, we first need to get them organized. The best way to think about it is like we're building a chemical family tree. It helps us see all the relationships and, crucially, the key differences that give them their own unique personalities. At its heart, the definition is actually beautifully simple. You just take a basic hydrocarbon, a simple molecule of carbon and hydrogen, and you swap one of those hydrogens for a halogen atom. And that's it. That one little swap creates this entire massive class of compounds. Okay, so right away, the family splits into two big branches, and it all depends on where that halogen attaches. In haloalkanes, the halogen bonds to what we call an sp3 hybridized carbon. Just think of it as a carbon atom that only has single bonds. But in haloarenes, it's attached to an sp2 hybridized carbon, which is part of a super stable, flat aromatic ring like benzene. This single difference in bonding completely changes their chemistry. It's a huge deal. So let's zoom in on that haloalkane, or sp3, side of the family for a second. Here we find three main groups. Your standard alkyl halides, then allylic halides, where the key carbon is right next to a double bond, and benzylic halides, where it's next to one of those aromatic rings. And on the other side, the haloarene, or sp2 family, we've got two main players, vinylic halides, where the halogen is stuck directly onto a carbon in a double bond, and the aryl halides we just mentioned, where it's attached directly to that aromatic ring. Okay, so we've got them sorted into families, but what really makes them tick? What's at the heart of their chemistry? Well, it all comes down to the properties of one very special bond, the bond between the carbon and the halogen. Right, this is the most important part. Halogen atoms are more electronegative than carbon. Basically, they're electron greedy. They pull the electrons in the bond closer to themselves. This creates what we call a polarized bond. The halogen end becomes a little negative, and the carbon end becomes a little positive. And that imbalance of charge, that's the key to pretty much all of their reactions. And this table shows a really clear trend. Just watch what happens as we go down the periodic table from fluorine to iodine. The halogen atom gets bigger, right? So notice how the bond gets longer, and at the same time, the bond's strength, or enthalpy, goes down. A carbon-fluorine bond is short and super strong, while a carbon-iodine bond is long and much weaker. This is so important for how they react. That trend in size also has a big effect on their physical properties. See, bigger atoms have more electrons, which means the temporary attractions between molecules, we call them van der Waals forces, get stronger. And this chart shows the result perfectly. As the halogen gets bigger and those forces get stronger, the boiling points go up, up, up. It takes more energy to pull them apart. But here's a neat little twist. If you have molecules with the exact same formula but different shapes, what we call isomers, the one with more branches will actually have a lower boiling point. Why is that? Well, branching makes the molecule more like a little ball. It gets more spherical, which reduces the surface area for those intermolecular forces to grab onto. Think about stacking bricks versus stacking spheres. Less contact means weaker forces and a lower boiling point. It's pretty cool.
All right, let's move on and see how this all comes together in their reactions. Because of that polarized carbon-halogen bond we talked about, haloalkanes are just perfect candidates for what I like to call the great chemical swap, a reaction chemists call nucleophilic substitution. So here's how it works. You have a nucleophile, which is just something with extra electrons that's looking for a positive charge to connect with. It sees that slightly positive carbon atom, and boom, it attacks the carbon and kicks out the halogen, which is happy to leave with its electrons. It's a super clean and efficient swap, and it's one of the most powerful tools chemists have for turning one type of molecule into another. Now, this is where it gets even more interesting. You have these special nucleophiles called ambident, which is just a fancy way of saying that they have two different spots that can do the attacking. A classic example is the cyanide ion. It can attack with its carbon atom, or it can attack with its nitrogen atom, and that leads to totally different products. And this slide shows exactly how we can control which one attacks. If we use potassium cyanide, KCN, which is ionic, the cyanide ion is free to attack with its carbon atom. This makes a really stable carbon-carbon bond, and we get an alkyl cyanide. But if we use silver cyanide, AgCN, which is covalent, the nitrogen atom is the one that's free to do the attacking, so we get an isocyanide instead. Same attacker, two different outcomes. It's just an elegant example of how chemists can control reactions. One of the ways this swap happens is through something called the SN2 mechanism. The best way to picture it is as a perfectly timed one-step dance. The nucleophile comes in and attacks the carbon from the back, at the exact same moment that the halogen leaves from the front. The result? A complete flip in the molecule's 3D shape, just like a strong gust of wind catching an umbrella and flipping it inside out. This inversion is so important, especially when making drugs where that specific 3D shape is everything. So we've seen just how unbelievably useful these compounds are, right? From life-saving medicines to the building blocks of industry. But there's another side to this story, and it comes from the exact same stability that makes them so useful in the first place. And this quote from the source material just nails the problem. That strong carbon-halogen bond we talked about, it makes these molecules really, really stable. They don't break down easily, which means when they get out into the environment, they can stick around for a very, very long time. And this leaves us with the big question, doesn't it? These compounds save lives and they drive entire industries, but they also create a serious environmental challenge. So the real takeaway here is the need for balance. How do we keep using their amazing benefits while also finding smarter ways to manage them and reduce their impact on our planet? That's really the big challenge for the next generation of chemists. Thanks for digging into this with me.